Our work, General Features of the Relaxation Dynamics of Interacting Quantum Systems, aims at advancing the current understanding of non-equilibrium quantum physics, which is much less understood than equilibrium quantum physics. We study numerically and analytically the dynamics of isolated interacting quantum systems that are taken out of equilibrium instantaneously. This instantaneous perturbation is known as a quench. We analyze the probability of finding the same initial state later on in time, which is known as fidelity and is also related to the Loschmidt echo. In this movie, we talk only about our results for the fidelity, but in our paper, you will also find results for the evolution of the channel entropy and of few body observables. The fidelity is the overlap between the initial state and the evolved one. The initial state is an eigenstate of a certain initial Hamiltonian. This Hamiltonian is quenched into a new final Hamiltonian, and the initial state now evolves according to the eigenvalues and eigenstates of the final Hamiltonian. We can then see that the fidelity is just the Fourier transform of the energy distribution of the initial state. If we know this distribution, we know the behavior of the fidelity. When the initial state evolves according to Hamiltonians that have only two-body interactions, such as the spin-half systems that we consider in our work, the energy distribution of the initial state depends on the strength of the quench. For a state close to the middle of the spectrum of the final Hamiltonian, we see that if the perturbation is very weak, the energy distribution is similar to a delta function, and the fidelity decay is therefore very slow. As the perturbation increases, the energy distribution broadens. When the shape becomes Lorentzian, the fidelity decay is quadratic for short times, as expected from perturbation theory, and then it switches to an exponential decay, since the Fourier transform of a Lorentzian is exponential. Finally, in the limit of strong perturbation, the energy distribution becomes Gaussian, and the fidelity decay is also Gaussian. Note that this Gaussian decay can hold all the way to saturation. This dashed line indicates the saturation point, that is the infinite time average of the fidelity. After this point, the fidelity simply fluctuates. The Gaussian behavior corresponds to the fastest fidelity decay in the scenario of quenches involving realistic systems with two-body interactions. But this decay can be even faster if the final Hamiltonian is a full random matrix. Full random matrices are not realistic because they imply the simultaneous interactions of many particles, but they serve to set the lower bound of the fidelity decay of quenched many-body quantum systems. In this case, the energy distribution has a semicircular shape, reflecting the density of states of full random matrices. The analytical expression for the fidelity decay now involves a Bessel function of first kind. It corresponds to the solid line in this figure, while the circles are numerical results. Well, we hope you will now enjoy reading the rest of the paper. Thank you for your attention.